What's up, guys? In this video, we are going to go ahead and take a look at the final exam review packet. It's going to be the first of a series of videos here, taking a look at these review problems that span from Unit 1 all the way through the end of the year. So this is a cumulative review of the year. These example problems are things that you could expect to see on the final, and it doesn't mean you're going to see these exact problems or problems with the same numbers, just expressed a little bit differently, but these are the concepts. So we're going to practice on concepts as we review these problems. So this is the first of a series of videos, and let's just jump right into the work. So in problem number 1, it says, which of the following represents the correct factorization of 4a squared minus 9b squared? Well, if you remember back to the unit where we worked on factoring, we said that a squared minus b squared is equal to the conjugate of a and b. So a squared minus b squared can be written as a plus b times, a minus b. So what we notice here is essentially we have to take a look at the square root of the first and the second terms in this expression. So the square root of 4a squared would be 2a. The square root of 9b squared would be 3b. So 2a minus 3b times 2a plus 3b. So the difference of two squares are the conjugates of the roots of the terms. In problem number 2, it says if 2x to the fourth minus if f of x equals 2x to the fourth minus x cubed, then which of the following is equivalent to f of I? So notice here that we have the substitution notation that I'm going to substitute I in for x. So f of I would be 2i to the fourth power or minus I to the third power. Now, if you remember your powers of I, we can start to simplify these, but you could also use the calculator to simplify in this case. So we can find the I button by hitting second and then the decimal. I to the fourth minus I to the third power is 2 plus I. So I to the fourth power simplifies to 1, I cubed simplifies to negative I, and there we would have 2 plus I. So you can do this either in the calculator or by hand. It says, which of the following quadratic functions would have zeros 2 and negative 4? Well, a couple of ways that we could do this. We could graph these individually and take a look at their intersections on the x-axis. So if you did so, let's go ahead and graph the first one. First one would be x squared plus 2x minus 3, and I can hit zoom and go to 6 for my standard window, and see here this intersects at negative 3 and 1. That's also because we can look at the factorization of this. So the factored version of this would be x plus 3 and x minus 1, giving us zeros, negative 3 and 1. So I could graph these individually one by one, or what I could do is factor them. So the second one factors into x plus 1 quantity squared. That's not going to give me the correct zeros that I'm looking for. The third one factors into x minus 3 and x plus 1. So there I would have zeros positive 3 and negative 1. That's not correct. And the fourth one factors into x minus 3 quantity squared, which would give me factors of positive 3. So in this case, none of these would have zeros 2 and negative 4. So you can find the zeros by factoring or by graphing. In problem 4, it says, which of the following would be a quadratic function with the vertex negative 3, negative 6, and a point 1, negative 2? So there's a couple of different ways that we can look at this one as well. The first thing is to remember the quadratic form for a vertex. So the vertex would be any shift to the left 3 and down 6. A shift left 3 and down 6 would be represented by equation A and equation A only. Remember, we have x minus h plus k. So this would be x minus a negative 3 and x minus 6. So I already know that the equations, or the options B through E are incorrect. Now I need to see if the option in A is correct. So what I could do here is I could go ahead and graph this, or I could use a method of substitution. Either of these methods would be a quick way to find out if the point 1, negative 2 exists on this function. And so if I graph this, sorry, I typed it incorrectly as I was talking, but it would 1/4 times x plus 3 quantity squared minus 6. If I look at the table here, I would see it does contain the point 1, -2, and so A would be my option. I could also just take a look at the graph in general and find that it does have the vertex here at -3, -6. Let's go ahead and take a look at some more multiple choice problems. Problem number 5. Problem number 5 says for the equation -1/8 times x plus 3 quantity squared minus h, which of the following is the location of the focus? Now remember, the focus has a relationship to the vertex. So in this problem, the TI-84 calculator is not going to help us. What we can do first is we can identify the vertex, and I'll label the vertex as V. The vertex is found by horizontal and vertical shifts. So this has a horizontal shift left 3 and down 8. So the vertex is going to be at -3, -8. Now if I sketch a version of this parabola, it's a negative parabola, so it's going to open down. There's a negative coefficient, so my vertex would be here at -3, -8. My focus is going to be underneath my vertex. It's going to be on the same x coordinate. So it's going to have an x coordinate of -3, so I can eliminate those options. It's going to be d units down. And this is where a is equal to 1/4d. So our a from the equation is -1/8. And 1/4d, technically the absolute value of a, so I'll just list this as a positive. So 1/8 would be the coefficient, that's a. If I cross multiply here, I would get 4d equal to 8, and then I can divide, d equals 2. So this focus is going to be 2 units, sorry, I created, sorry, there we go, that is correct. This focus is going to be 2 units below the vertex, 2 units below the vertex. So if a vertex is at -3, -8, I'm going to use move down 2 units, and so this would be a change on the y. This would be at -3, -10. So our answer here is B. In problem 6, it says for the equation x minus y squared equals 0. Which of the following gives the equation of the directrix? So in this case, we probably want to rewrite our equation to get x by itself because the y is being squared. So x equals y squared. This is going to be a parabola as there's no horizontal or vertical shifts. A parabola centered at the origin, opening to the right as it is positive. So the directrix is going to be, in this case, behind or to the left of the vertex as it is outside of the parabola. It is going to be d units from the vertex. So like we saw before, the focus is d units, the directrix is also d units away. And d can be found again using the equation. The absolute value of a is equal to 1/4d. A in our case here, now that this is a horizontal parabola because x is by itself and y is squared, a would be the coefficient of y squared, which is 1. So 1/4d is equal, 1 equals 1/4d. If I cross multiply, 4d equals 1, divide by 4, d equals 1/4. So this would be 1/4 unit to the left of 0, 0. So 1/4 unit to the left would be x equals -1/4. Answer would be D. Taking a look at C, it says, which of the following is a factor of 2x to the 4th plus 4x cubed plus 2x squared plus 16x minus 24? So what I could do here is try to factor this by hand, taking a look at GCF and then getting into the method of finding the P over Q as we did in polynomials. But an easier way to do this is to take a look at the graph of this function. So remember that the factors give us zeros. So what I'm going to go ahead and do is take a look at the graph. It's going to take me a moment to type this in. And I'm going to keep it on the standard window for right now to try to find the X-intercepts. So I see I have at least 2 X-intercepts here. If I widened out, let's zoom this out real quick. Try to get a better picture of the graph. we can see that it's not returning back to the x-axis. So the two intercepts that we have there are our two real answers for x. So what we can see is that I have x equals 1 and x equals -3. And so what I know for sure is that x equals 1 comes from the factor x minus 1. So x minus 1 has to be a factor at least. X equals -3 comes from the factor x plus 3. And so that's not an option there. We're not sure about imaginary units. We're not sure if the imaginary unit 3i is a factor or not. And we can tell that +2 is not, because this does not intersect at -2. So our one option we know for sure is a factor is C. In 8, it says, which of the following would be a possible rational root? Remember, possible rational roots of polynomials come from P over Q, where P is factors of the leading coefficient divided by factors, P is factors of the constant divided by factors of the leading. So what I can do here is I could take a look at the factors of 7 and the factors of 8. So P are my factors of the constant, and so this would be positive and negative versions of 1, 2, 4, and 8. They are factors of 8. Q would be factors of 7, so this would be positive and negative options of 1 and 7. So P over Q, all possible rational zeros. These aren't necessarily going to all be zeros, but these are the list of possible rational zeros for the polynomial would be 1 over 1, 1 over 7, 2 over 1, 2 over 7, 4 over 1, 4 over 7, and 8 over 1 and 8 over 7. So this set, all positive and negative versions of the set would be the possible rational zeros. And so what we see here is positive 2 over 7 exists in this list. That would be our possible rational root. Taking a look at number 9, it says, which of the following is equivalent to 9a squared plus 16a squared? So remember, with square roots, we can simplify this by adding together the terms in the radical expression, the radicand. So this would give us 25a squared. And remember that we can essentially root terms as separate pieces. So these are square roots. The square root of 25 would be 5, and the square root of a squared would be a. So 5a would be the simplified version of problem number 9. In problem 10, it says, which of the following is equivalent to the cubed root of 64a to the 16th power? Now remember, with cube roots, we're taking a look at numbers that can be cubed. So what I could do is I could rewrite this as 4 cubed. So 4 times 4 times 4, or 4 cubed, is 64. Now I'm going to take 16 and I'm going to split it up into a to the 15th times a. A to the 15th times a is a to the 16th. But more importantly here, I can write a to the 15th as a to the 5th cubed. So breaking down a to the 15th as 3 versions of a to the 5th allows me to simplify this. Remember, cube roots and cubic exponents are inverses of one another. So if I cube root 4 cubed, I get 4. If I cube root a to the 5th cubed, the cube root and the cubed would undo each other, leaving me a to the 5th. Now I do have an a left over inside the cubed root, so my answer would be C here, 4a to the 5th times the cubed root of a. In problem 11, it says, which of the following is the domain for the function x equals negative, or f of x equals the square root of negative x plus 5 minus 2. So algebraically, remember that the input value for a domain must be greater than or equal to 0. So if I solve this, I would subtract 5 and then divide by a negative, and I get x is less than or equal to 5. Because this is a multiple choice, I could also do this problem graphically. So I could take a look at the graph by inputting the equation into my graphing calculator and making sure I'm in the standard window and looking at the graph. So here I can see that this graph has values to the left of this point right here, and this point would be 5 on the x-axis. Now I would want to check the table to make sure that it does have a value at 5, and it does. It is equal at 5 and has values to the left, or negative from 5. In problem 12, it says, assuming a is greater than 0, so we're not dealing with any imaginary units here, which of the following is equivalent to 27a cubed, the square root of 27a cubed plus a root 3a. Now remember, I cannot add together these roots unless they are exactly the same. So remember, you can only add together roots that are the same type of root, having the same index and the same radicand. So what I can do is work at simplifying the first root here. So I'm going to break this into 9 times 3. So I'm going to break 27 into 9 times 3, and then also into a squared times a. Because now that will allow me to square root some terms. The square root of 9 would be 3, and the square root of a squared would be a, leaving me with 3a left with inside the square root. Now I can add these together by combining the coefficients. So if I combine the coefficients, 3a plus a would be 4a. So remember, with constant terms that are equivalent, if we add them, their coefficients would be added together. So 3a plus a would give us 4a. Taking a look at another example, problem 13 says, how many solutions exist for the below system of equations? So we could look at solving this algebraically, but probably the easiest thing to do would be to solve this graphically. So I'm going to go ahead and rewrite these equations in terms of y. So I'm going to add 2x to both sides of the first equation. In the second equation, I am going to subtract x squared from both sides, and then square root both sides to get y by itself. Remember, when I create a square root in the process of rewriting or solving an equation, I need to make sure I include the plus or minus versions. So now I can take a look at these graphs. Remember, solutions to a system of equations are any intersection points. And so this just asked for the number of solutions. So notice here I'm typing in a positive version of the square root of negative x plus 5 and a negative version of the square root of negative x plus 5 to account for my plus or minus. So as I do so there, I can take a look at the graph, and here's my line. And the other equation is a horizontal parabola, and we can notice here that it has 2 intersections, and so my answer to this question would be there are at least 2 solutions. We could also tell that both of those solutions would be real solutions, real numbers. If we wanted to find the solutions, we could find the intersections on the calculator. Problem 14 says, which of the following best describes the below system of equations? So we could do this both algebraically or graphically. I'm going to go ahead and do it algebraically because it's a little bit quicker to do algebraically. If I take the first equation and I multiply it by, let's make it multiply by -2. This would give me a negative 6x plus 8y equal to -4. I chose to multiply it by -2 because now we see that the variable, at least one variable, is going to cancel out when combining these equations through addition. In this case, -6 plus 6x would be 0. -8y plus 8y would be 0. And so if I combine these through addition, I get 0 equals -3. And so what we know here is that this problem is not going to be correct. This is not going to be a solution, and thus we have an inconsistent system of equations. Now, if I tried to do this graphically, what I would find is I would have parallel lines, and when they do not intersect and there is no solution, this system would be what we consider inconsistent. Let's take a look at 2 more problems in this video. So in problem number 14, it says, which of the following is a solution to the below system of equations? So here we have to find the solution. So similar to the problem we did in 13, I'm going to go ahead and graph these. So the second equation is already written in the appropriate form to graph. With the first equation, I'm going to rewrite it through first subtraction of the x squared term, and then by creating a square root. So this is actually the same example equation as we saw from above. So That equation is already in my calculator. Again, remember when I created the square root, I need both plus or minus portions of the square root. And so I actually entered these incorrectly. Let me go back and do the previous question, 13. I did make a mistake on 13. This should insert a squared there. So hopefully you did catch that when I was working on this. But I should have had it x squared here. So let's revisit problem 13 real quick. I did not type in the equations correctly. So this is what the actual graph should look like. We have a circle graph, and then we have a line graph. And if I zoom in here, I can see that it looks like it probably intersects once, but let me zoom in over next to where it looks like we have that intersection. And I can see that there is one little intersection point here. And so this actually, problem 13, did not have two solutions. It had one. So hopefully you guys caught that mistake, but there we can correct it. Sorry about that. In problem 15 now, rewriting the equations, I had the same equations that I had before, plus or minus the square root of negative x squared plus 5. So those two equations are in there as y2 and y3. Again, two lines because I have one positive and one negative. Let me go ahead and input the the other equation, so negative 1/2 x squared plus 1, and I'm going to hit zoom and hit standard so I can go back to the normal window here. And I can see that there appear to be two intersections here. So I'm going to zoom in a little bit. Let me adjust my windows. I'm going to make this -3. Let's make this -4 on the x. Oops. To +4. Here I'm just choosing some numbers that are going to create this a little bigger picture here. And I hit zoom fit so that I could better see my intersection points. So there are two. This said which is a solution. So I only need one solution. I can hit second trace. It gets me the calculate menu and go to intersect. I'm going to move over on my cursor here. I'm going to move over close to the intersection point. Now when I hit enter, it's going to put me on the curve above. So I'm going to hit the down arrow key so it puts me on this curve below and find the intersection. And this intersection would be 2, -1. That does show up as one of my solutions. So my solution is the intersection point of these two equations. Now again, you could have found that algebraically, but here's a quick graphic solution. In problem 16, the final problem we're going to look at in this video, it says which of the following is the solution to the below system of equations? So here I have a system of equations, a 3-variable system, and I could solve this algebraically if I wanted to, but a quick way to check these, to see if these are solutions, is actually to substitute. So I'm going to take this first equation that's listed right there, and I'm going to substitute in the x value of 1, the y value of 2, and the z value of 0, and see that if I substitute this in correctly, -6 times 1 minus 2 times 2 minus 0, this would give me 17. So this is not a solution to the first set. So I'm going to get rid of that option. I'm going to repeat the same thing, but I'm going to change my input values to 2 for x, in the second option, 2 for x, leaving 2 for y, and now selecting 1 for z. This does work out for the first equation. I do also need to make sure that it works out for all equations. So I'm going to get 5 times 2 plus 2 for y minus 6 times 1 for z. That equals 6. It does not work out for the second equation. So this is not a solution. Let's try again here. Let's take this first equation and let's use 2, 3, and now minus -1 would be +1. So that does work out for the first equation. Let me take the second equation, and I would have 5 times 2 plus 3 for y this time, minus 6 times -1 for z. That works out for the third equation. So now let's finally take a look and see if it works out for the fourth equation. So here again, I'm just doing substitution for x, y, and z to determine if these are solutions. And when I substitute in for z, it does match, or for the third equation, it does match the output value with all inputs substituted in. And so here I have the correct solution. So I can check this through substitution. This is going to be a good place to stop for video 1 in the series. If you want to see more example problems from the final exam study guide, check out the other videos. As always, thank you guys for tuning in, and I'll see you soon.